Hello, and welcome to Lesson 24 of this Introduction to Differential Equations with Wolfram U. Many interesting physical systems can have discontinuous forcing functions in the differential equation that describes their behavior. Now that we have an understanding of discontinuous functions, we will discuss how to solve differential equations with such terms using the Laplace transform. Let's take a look at an overview of this lesson. We discussed how to construct and transform discontinuous step functions in the previous lesson. Using what we have learned from that lesson, we can solve differential equations with discontinuous non-homogeneous terms. Such equations appear in many physical systems. For example, a spring mass system can have a discontinuous non-homogeneous term due to an external force, or in electric circuits where the flow of current may not be continuous due to a switch. As we can see in the plot here, the solutions to differential equations with discontinuous non-homogeneous terms can have behavior that changes very abruptly at certain locations, while the solution has a complicated shape that is not an obvious linear combination of sines, cosines, and exponentials. As a first example, let's find the solution to the differential equation here, subject to the initial condition that the solution equals 1 at t equals 0, and the first derivative equals 0 at t equals 0. The right-hand side of the differential equation is the discontinuous unit step function shifted 1 unit to the right, so that the discontinuity occurs at t equals 1. As we will see, solving such differential equations can be done quite easily using the Laplace transform. To use the Laplace transform to solve this initial value problem, first define the equation in the Wolfram language. Now that we have the equation defined in the Wolfram language, apply the Laplace transform to the differential equation. When taking the Laplace transform of the equation, terms involving the initial conditions are present. These terms can be replaced with their numerical values given by the initial conditions in the statement of the problem. With the Laplace transform taken and the initial conditions substituted into the result, the next step is to solve for the Laplace transform itself. We now have an expression for the Laplace transform of the solution, so we can apply the inverse Laplace transform to obtain the solution to this differential equation. We can observe the effect of the non-homogeneous term on the path the solution takes. The non-homogeneous term makes the first trough in the function a little more shallow, and causes the function to come to a non-zero equilibrium point. If the discontinuous term were not there, the first trough would occur at a negative value, and the solution would come to an equilibrium point at large values of t near 0. Now let's compare the result we found with the result from d-solve value. We can see that the solution d-solve value found and the solution we found using the Laplace transform are identical. Now let's consider solving the second-order differential equation here, where the non-homogeneous term is now the sum of two unit step functions. Once again, we are given initial conditions on the value of the solution and its first derivative at t equals 0. Plotting the non-homogeneous term shows that it is 0 when t is less than 5. It increases linearly until t equals 15, then becomes the constant 1 when t is greater than 15. We will again solve this initial value problem using the Laplace transform, so we will first need to define the differential equation in the Wolfram language. Now that we have the equation defined, apply the Laplace transform to the entire differential equation. We can see that terms involving the initial value of the solution and its first derivative at t equals 0 are present in the Laplace transform of the differential equation. Therefore, we can substitute the numerical values for the initial conditions that are given in the statement of the problem. We now have an expression involving the Laplace transform of the solution, which can be solved for that transform. With the Laplace transform of the solution obtained, we take the inverse Laplace transform to arrive at the solution of the initial value problem. We have obtained the solution to this initial value problem using the Laplace transform. Now let's look at the solution along with the non-homogeneous term. We can see that we get an oscillating solution when the non-homogeneous term is zero. As the non-homogeneous term increases, the oscillations continue, but with the average value of the oscillations increasing. When the non-homogeneous term levels off at 1, the oscillations level off as well, but with the average value shifted up slightly. We can use d-sol value to verify the result we found using the Laplace transform. It is seen that the solution from d-sol value agrees with the result we found using the Laplace transform. As a final example, let's consider the second-order non-homogeneous differential equation here, subject to the initial conditions that the solution is equal to 1 at t equals 0, and the first derivative is equal to 0 at t equals 0. Plotting the non-homogeneous term shows that now it looks like a box function, where it is 0 if t is less than 5 and greater than 20, and equal to 1 between those values. To solve this initial value problem, first define the equation in the Wolfram language. To solve the differential equation, take the Laplace transform of the entire equation. Then, replace the y of 0 and y prime of 0 terms with their respective values. Now we have an equation involving the Laplace transform of the solution that we can solve for that transform. With the Laplace transform of the solution found, the solution to the initial value problem can be obtained by using the inverse Laplace transform. Now that we have the solution, plot it along with the non-homogeneous term to see the interesting path that it takes. We can see that the solution has a damped oscillatory pattern when t is less than 5 and when t is greater than 20. The function oscillates between 5 and 20 as well, but there is an abrupt jump in the function. This result can be confirmed with d-sol value. We can see by plotting that the solution of the two are indeed identical. Let's compare the solution of the previous problem with the solution if there were no homogeneous term. To make this comparison, first define the homogeneous equation, then solve the equation with d-sol value. It can be seen that the large jump in the solution between t equals 5 and t equals 20 is no longer present in the homogeneous solution. Instead, the oscillations seen in the solution get damped very quickly, where they are barely noticeable past t equals 30. In this lesson, we used our knowledge of step functions to solve a certain class of differential equations where the non-homogeneous term is discontinuous. By applying the Laplace transform to the non-homogeneous differential equation, we were able to obtain a solution to the initial value problem quite easily. With these methods, we can describe a wider variety of systems with differential equations than we had before.